In this section, we're going to take a look at hypothesis tests for a single proportion. So this is going to extend from the work we did with confidence intervals. So how it connects is that with confidence intervals, it was all about having the sample data, and with that we can make an estimate for the value that's occurring in the population. What's the true population value? What we do in this section is a similar setup where we have sample data, and what we want to do is test a hypothesis that we have about what's true for the population. Is it more than some value? Is it less than some value? And with these, we want to prove statistical significance. So what we're going to do in this first video is just kind of get a feel for the pieces that we'll see as we go through a problem, and we'll kind of end up going through a hypothesis test here. If everything's not clicking yet, that's totally fine. There's going to be about 5 steps to our work that we do with these hypothesis tests, so we'll talk about the steps, and then we'll even have videos that break down how we approach each step and what are we looking for with each of those steps as well. Okay, but how it connects to our inferential statistics that we're doing is the idea that we have information about some sample proportion. That's what I'm trying to say. So we have information from a sample. That's something we can collect easily. Hopefully it's a nice random sample. And what we want to understand is, what does that tell us about our population proportion? So again, with inferential statistics, we want to avoid collecting population data, but something we should have is some assumption about what's happening in the population. So let's take a look at this scenario here. I flip a coin 50 times and get 75% heads. Is this evidence that the coin is unfair? The idea being, I expected to get close to 50%. Maybe not exactly 50%. We could be a little above, a little below, but 75% seems pretty high up there, and that would have me scratching my head of, ooh, is this coin actually 50-50? So some information we're giving here, we have some sample data. So we have a sample size. We have a sample proportion. And then we want to find, is this evidence? That's something that we'll be looking for here, because what we're running is a test. And with these tests, we want to find evidence. And we want to see if it's evidence that the coin is unfair. So as we use P and P hat here, let's go ahead and have P represent the proportion of heads on this coin. So if we flip this coin infinitely long, what's the proportion of heads? If it's a fair coin, we would expect 50%. So our assumption is, this is some random coin. We assume that it is a fair coin, which means we should have 50% chance of heads. This part right here, this assumption, we call this the null hypothesis. And the notation that we're going to use, again, I'm just going to show everything here. We're going to do this many more times with breaking it down. But the null hypothesis, how we would write this out is we would go capital H with a little subscript of 0 there. That represents our null hypothesis. And our null hypothesis is that our population proportion, P, is equal to 0.5. That right there is our assumption. So if we ask for a null hypothesis, what I have in green there, at H sub 0, P equals 0.5, that would be my null hypothesis. Now what I want to prove, or what I'm trying to find evidence for, is that we have an unfair coin. So what I want to see is, I see that 75%, and I want to show that the proportion is significantly larger than 50%. And being significantly larger is an important piece here. Let me go ahead and write that down. To prove that it's an unfair coin, we want it to be significantly more than 50% heads. So the significance part is where the statistics comes in. We want it to be statistically significant. Because if we just want to prove that it's more than 50% heads, well, 75% is more than 50%. Cool, done. But to show that it's significantly larger, we need a little bit of math to help out. So this right here is called the alternative hypothesis. So it always links with what I want to prove or what we're looking for evidence for. So alternative hypothesis. And with this, in terms of notation, what you'll see is a capital H with a subscript of capital A. Sometimes you'll see a 1 there. That works great too in terms of notation. It's just nice to have the A to link with alternative, but either way is fine there. And then it's that we want this population proportion more than 0.5. So null hypothesis, P is 0.5. Alternative hypothesis, P is more than 0.5. So how would a fair coin flipped 50 times behave? So what we're doing here is we're saying we're flipping a coin 50 times. If it is truly a fair coin, what would this look like? Or you can think of this using the terminology we're seeing up above here is if that null hypothesis is true, how does P hat, our sample proportions, behave? Meaning, if our assumption is true, then how should these sample proportions behave? We're seeing how one sample proportion behaves, but if it's a fair coin, how would all other sample proportions behave? So if we need to understand how sample proportions behave, that means we need a sampling distribution of proportions. So what we have here is we have an assumed proportion for our population, P is 0.5. We have a sample size we want to work with, N of 50. And with that, we want to build a sampling distribution. So for our sampling distribution, we need a mean and standard deviation. Mean is equal to that population proportion. And then standard deviation, we have a little bit of work to do with, we'll have a 0.5 times 0.5 over our sample size of 50. So we're getting a 0.0707. Okay, so what that would do, and in fact, let me go ahead and get a nice little picture for us coming from Staplet here. So in Staplet, we have a normal distribution. We haven't actually proven we have a normal distribution yet, but that will come up in a little bit. Let's go mean of 0.5, standard deviation of 0.0707. Want that distribution, and I just want to grab a little picture here for us so we can refer back to it. Okay. So with that, just a little moving around. Okay, there's my picture. Beautiful. So what we have here by building this sampling distribution, what this represents is this is a distribution of P hat of our sample proportion if, or let's go with assuming. I'm going to keep with that word of assumption. Assuming that null hypothesis is true and using sample size of 50. There's two pieces that are important here. This is built under the assumption of our null hypothesis. We're assuming that in this case, that means that we have a fair coin being flipped here. And also that we're using the same sample size. Our sample sizes should match because as we talk about, sample size affects things. And you can see it in the standard deviation with that denominator there where we plug in our sample size. So we want to make sure that stays consistent. And then what we can see is how all sample proportions should behave under that null hypothesis. Okay, so let me go back to my question here. How would a fair coin flipped 50 times behave? It would behave just like this distribution. We expect 50% to come through, maybe 57%, 64 starts to get out there, or like about 43 or about 36. So we can get an idea of what proportions we expect to come through, and then we start to see some extreme values out here in the tails. So, my next question, where does my sample land in comparison? Does it have a high or low probability of occurring? So now what we do is with this, let's check out where our specific sample proportion is landing of 0.75. Because we knew it was more than 50%, but how much more than 50%? Or sorry, yes, more than 50%. So as we can see, if we go up to this right-hand side, we see 71%, but 75% is out over here. And that is telling me it has a low probability of occurring. Almost impossible under this distribution that's so far out there. But let's make this a little abstract of this. What if it was a high probability versus low probability? And in fact, let's go ahead and start with that the probability is small. It had a low probability because that's what we're actually seeing here. So if I have my distribution, and this distribution is all about the null hypothesis. I'm just going to put that there because that's what that image represents. That's our null hypothesis. And then I'm going to see where 0.75 lands, and it is landing way out here. This probability, though, or it's not just the probability of that location, because as we talked about with normal distribution, we can't find probability of just a single location. So what we end up doing is finding the probability of that location or more extreme. So what we end up doing is going to that 0.75 or even larger. So it's going to be this little right tail area that we use to evaluate things. So what does it mean to get a probability that's so small? And a little word I'm going to sneak in. Actually, I'm going to go through the explanation, then I'll bring back a definition for us. So what this shows me is our sample that we observed is unlikely under the null hypothesis assumption. Under that null hypothesis, or if it was a fair coin, we saw something very unlikely. What this means is that it is statistically significant results. Seeing such a low probability come through is statistically significant. And what that means we get to do here is we say we reject the null hypothesis. What we essentially do is say this null hypothesis just isn't correct for the sample we observed. We saw something so unlikely that we probably don't have a fair coin. So we would want to throw out that assumption that we have a fair coin. And then what we end up with, which this is the big thing we want to end up describing in a sentence at the end, is that this is evidence for the alternative hypothesis. Or in this case, evidence that we have an unfair coin. Okay, so let's tie that together. We have a distribution built around our null hypothesis, and we're seeing our sample land way out in the tail, which means the probability of that sample, or more extreme, is a low probability. And we'll talk about what the cutoff for low versus high probability is in a later video. But all of that means is that the sample we observed is unlikely under that null hypothesis, which means we're seeing something statistically significant. So we reject the null hypothesis, and claim the alternative hypothesis. We essentially get to go back up here and say, this isn't working because we saw a sample that was very extreme if it was a fair coin. Now, we got to note, not impossible. It is not impossible to take a fair coin, flip it 50 times, and see 75% heads. But statistically, the likelihood is so low that we end up making a claim for this alternative that we have evidence that this coin is unfair and has a proportion of heads more than 50% of the time. Let's talk about if we saw something a little bit different. So we saw this is the true case that's coming through in this scenario. The probability is small. But what if? What if that wasn't the case? Or what if we were testing that we had a sample proportion of 0.62, something like that? So what if we go to our distribution that's built under that null hypothesis? So same distribution, all with the assumption that we have a fair coin, we expect 50%. But what if my cutoff was 0.62? Or what if when we built this distribution, 0.75 was actually a lot closer? So what if our cutoff was actually closer over here? So the area we're interested in is an area to the right. We want to find the probability of that value or more extreme. And again, we'll talk about a cutoff for what's considered large versus small. But under this scenario where we're seeing a larger area come through, that means our sample is fairly likely under the null hypothesis assumption. Assuming this is a fair coin, we saw something that could not easily happen, but fairly likely that we would see that pop up, which means our results are not statistically significant. While they don't line up exactly, it's not extreme. So what we say with this is we fail to reject the null hypothesis. And some weird wording here that's important to clarify, though. We never, ever accept the null hypothesis. That's not what we're trying to prove here. We just set up the null hypothesis as some assumption, but it's all about the alternative hypothesis. We either have evidence or don't have evidence for the alternative. But the null hypothesis is just kind of part of the process. We can either throw it out or we don't have enough evidence to throw it out. It's weird wording, but that's what we have with this section. So, fail to reject the null hypothesis. Never say accept the null hypothesis. That's not what we're finding evidence for. But where the importance is all about that alternative hypothesis, we would say not sufficient, not enough evidence for the alternative hypothesis. It could be that this is an unfair coin, but we're not seeing statistically significant results enough to confirm that. So, not enough evidence for the alternative, and with that we say there's not enough evidence that we have an unfair coin here. Okay, one tiny vocabulary before I wrap up this video. This area is what's determining which conclusion we make here. And all of these things tie together for making this conclusion, but how we know which conclusion we make is all from the largeness, or rather smallness, of this area coming through. And that area is called our p-value. P-value. So what this comes down to is on the left-hand side here, this is the case for when we determine the p-value is small. And on the right-hand side, it's when we see the p-value is not small. So where we're going to end up is using stats, we're going to calculate the value for the p-value, and then from there determine whether it's small or large, and then from there we can write up a conclusion. So there's a lot of information there. In the next video, I'm going to go through the full hypothesis test for this scenario, but hopefully this lays kind of a nice foundation before we jump in there.